Working with datasets is a crucial skill for many professions. Doctors, engineers, data scientists, and many more all have to analyze data. And one of the most important aspects of data analysis is nonlinear regression. Most of the data collected in the real world is not linear, and it has to be transformed in the right way before being analyzed. I have taken an engineering course that explores the use of curve fitting using nonlinear regression in Excel and MATLAB. Today, we'll talk about the use of Excel. So, to get started, all you really need is a computer with internet access in case you do encounter any problems. Next, Microsoft Excel version 2007 and later. The earlier versions do not support some of the tools we'll be using. And finally, a dataset to analyze, since you can't do data analysis without a dataset. Here I have a bunch of x and y values that represent some correlation between them. Our job is to find the correlation and make a model, which is just an equation that we can use later to extrapolate values outside of the given range. In order to get a model, we'll first have to determine what type of function best suits the data. Most of the time this can be done visually, so the first thing we'll do is plot the data. In order to do that, we select the Insert tab, then choose the Insert Scatter option. Here it's important to avoid using anything but a scatter plot, since that's the only plot in Excel that allows for the scaling of both axes, x and y, which is what we'll be doing to determine the function type. As you can see, the data is not very linear, so our job is to find the right modification to linearize it. University of Columbia suggests using log transformations. To do that, we'll be using base 10 logarithms of all of our values. First, the x column. Use the function log10 and plug in the first x value. Now there are 4 different columns, so we'll have 4 different charts. So let's get to plotting the 3 remaining ones. First one will be an exponential chart. To do that, we'll be plotting the original x values against the log of y values. Next up, a logarithmic chart. It's the exact opposite of an exponential, so we'll be plotting the log of x against the original y. Finally, the most complicated function is the power function. To plot it, we'll be plotting the log of x against the log of y. So now that we have a straight line, we can use the built-in function linest, short for linear estimate, to produce the slope and the intercept of our modified values. So first we select the log y as our known y's, and the important thing to avoid here will be to use anything but these values, since they will produce the wrong coefficients and we won't be able to make a model with them. Next, select the known x's, which is the log x. And we see that our formula spills into 2 tabs. These are the b and a coefficients of our line equation. Depending on the function type, you'll have to modify these coefficients in one way or another, unless the dataset is linear, which in this case it is not. According to University of Maryland, for the power function, the most important coefficient is b, so it remains unchanged. Now, since we use base 10 logarithms, we'll raise 10 to the power of the coefficient a. Finally, we have everything we need to create a model equation and use it to estimate the values of the data, so we can see how good our model is. The power function is a function of type a times x to the power of b. So we use the modified a coefficient, which is 10 to the power of a. Remember to press F4 on all of our coefficients, or else your new column of data will be full of errors. We multiply that by x, which is our original data, to the power of b, which is our unchanged coefficient. Again, press F4. Now let's take a look at another model. This one was taken from Lumen Learning, and this time it's of a different type, but we still don't know which yet. I've already plotted the data to save us time, and as we can see, the straightest line is on the exponential graph. So let's get to it. As you may remember, the exponential graph was produced by plotting the log of y's against the raw x's. So when using linest, we plug in the log y column and the raw x. We get 2 coefficients, b and a, and in the exponential equation, both coefficients are of equal importance, so we'll be modifying both of them by raising 10 to their power. Now that we have everything we need, we can make our model. The exponential function is a function of type a times b to the power of x, unlike the power function. So we type a, which is our modified coefficient, times power. First we select b, and then the x. Finally, you may be guessing that we'll take a look at a logarithmic model, but not so fast. It looks like there are two almost identical lines on two different charts. This dataset is either linear or logarithmic, and there is no way for us to determine which visually. What we have to do is make two new models, linear and exponential, and use a built-in Excel function to calculate the correlation coefficient, otherwise known as R-squared. First, let's make a linear model. Linear model requires no modification, so when using linest, we just plug in the raw y's and the raw x's. The linear function is of the type b times x plus a. As you may recall, the logarithmic plot was made plotting the log of x against the raw y. So this is what we'll be plugging into linest. First the raw y's, then the log of x. We get two coefficients, and to make a model, we have to remember that the logarithmic function is of the type b times the log of x plus a. Finally, to find out which model suits the data better, we'll be calculating the R-squared. The Excel has a built-in function called RSQ, and the known y's for this function will be our model data, and the known x's will be the y's that we got from the dataset. An important thing to remember here is that on a small scale as such, the difference between the R-squared values may not seem like a big deal, but when datasets are comprised of tens of thousands of values, even a small change can make a big difference. Finally, we have covered 4 of the most common function types that you'll encounter while working with datasets, and I hope you enjoyed this tutorial.